Welcome everyone to this Zero Energy Project webinar on how to design and build affordable zero energy houses. This webinar will take about an hour, and I appreciate you taking the time to invest in this information. My name is Bruce Sullivan. I've been involved in the movement to improve energy efficiency in buildings since the early 1980s. I've seen many things over those years, many small incremental improvements. But now it's become clear that we can make buildings that create as much energy as they use. So the question isn't whether we can design and build zero energy buildings, but how to do it and how to do it affordably. So that's what we're going to talk about for about the next hour. We'll begin by talking about what is net zero, and then we'll go through some of the elements of a zero energy home. My intention is not to give you an exhaustive design and construction guide to zero energy homes, but really to talk about this at a fairly high level and emphasize the elements that can be made affordable. We'll have a lot of very detailed information on the Zero Energy Project website. So if you are interested in one of the ideas that I have, you can usually go there and drill down and get some details. And finally, the most important issue is how can we finance these homes so that anyone can enjoy them. Just a note about why we do this. Buildings represent 40 to 50% of the carbon emissions in the United States, and so buildings are a very important sector to address in terms of reducing the carbon emissions from those buildings. We also see that transportation is a huge piece of that pie. Buildings and transportation really work together in a lot of ways, and so we'll talk a little bit about that, but most of our comments today are going to be about buildings. Society has to provide the needs of that building. All the energy, the water, the waste disposal resulting from that building is something that really burdens society for as long as that building exists. So we can turn this around and say, shouldn't buildings, new buildings especially, take care of their own resource needs, and then over the next 100 years that building exists, it will be able to support itself, and with any luck we can actually have that building support others as well. Climate is always an issue when we are talking about zero energy construction. A zero energy building in Minneapolis may look a lot different than one in Miami. One of the things that you really need to focus on is what it takes to be zero energy in the location that you're building, and obviously the climate has a lot to do with that. Where I live in Oregon, the average house uses the equivalent of 29,000 kilowatt hours a year. This is all the energy that building would need for space heating, cooling, water heating, lights, appliances, and everything. 29,000 kilowatt hours a year would take a solar system that's about 24 kilowatts in capacity. So if you tried to make the average house a zero energy house simply by slapping some solar panels on the roof, probably wouldn't work. You probably wouldn't have enough roof space to make that happen. So that leads us to this idea that many of you have probably heard about. I call it the energy pyramid. The base of that pyramid is really building a very energy efficient shell with high levels of insulation, very tight construction. The windows are going to be highly efficient. Also the equipment, the space heating and cooling, the water heating equipment is all going to be very efficient, and that means that at the very peak of that pyramid, it doesn't take too much solar technology to generate enough electricity to run all the equipment in the building. So in other words, the top of the pyramid, the amount of renewable energy you need to provide is a lot less. Now this has been kind of the traditional approach, really because solar panels and wind generators have been very expensive. That has changed dramatically in the last few years, to the point where some builders and designers have decided to turn the pyramid on its head, and they decide how much solar they can generate on the roof of the building, and then design the shell of the building and the equipment selection to match that capacity. Now, I don't think that's the least cost approach, but it is certainly one way to approach the problem. And that leads us to the next idea, that how do you make the decisions about mixing and matching the different components to get to the goal that you want? And that's where a computerized energy model comes in. Energy modeling is a way that a computer can estimate the amount of energy that is consumed in the building, and also most of the models will estimate solar generation on the building so that you can really come very close to getting to your zero energy goal. Now, computer models are always wrong to some degree. They're estimates, and so you have to take them with a grain of salt. But nevertheless, it's a really great way to put numbers on some of the things that, some of the decisions that you need to make along the way. Modeling is currently used more as a compliance tool for energy efficiency programs such as Energy Star. But you can also use modeling to optimize the selection and the design of different components of the building. So you can look at how much energy is it going to save to go to a 10-inch double wall, or how much energy is it going to save to put it 2 inches of foam insulation on the outside of the walls, and then compare those two options along with the cost to build those two options, and then you can find the least cost combination of features. And this is also true for mechanical equipment and windows. You know, do I need to go to a triple pane window, or can I use a really good double pane window? So the energy modeling step is super important when you start the process, and is a way to not only optimize the techniques and the materials in the building, but also the cost in the building. One of the things in design that makes a lot of difference is the heat loss of the building relative to the shape and size of the building. We all know that a more compact space has a lower surface area to volume ratio. Heat loss occurs from the surface of the structure, so having a lower surface area to volume ratio is going to improve the efficiency of the building, reduce the heat loss. And so this is just an illustration of doing that. It's kind of why, you know, a lot of the passive houses you see are fairly boxy two-story buildings, because they're trying to really optimize that shape. Doesn't mean that you can't have corners or architectural interest, but it does mean that this is one way that's fairly inexpensive to get better performance out of a building. The other thing that simplicity will bring you, if in simplicity in your architectural design, is it's a lot easier to implement a lot of these shell measures like insulation and air sealing on a simpler shape. If you have lots of corners and dormers and things shooting out in all directions, all those things create complexity in terms of insulation and air sealing as well. So simplicity makes a lot of sense. It saves money, and it improves the efficiency of your building. We're always concerned in zero energy with the bottom line consumption. And so some people get efficiency and consumption confused, and so I'd like to make a little clarification here that we're really concerned about the number of kilowatt hours of energy, or the number of BTUs of energy the building is using. We're not concerned so much with the efficiency rating. So for example, kilowatt hours per square foot would be an efficiency measure. We don't really care what the square footage is. We just want to make sure that the kilowatt hours are as low as possible. To illustrate this, we did some studies about 10 years ago in this research project with the Oregon Department of Environmental Quality, where we did life cycle assessment on a number of different buildings. And so this was kind of one of the surprising results of that. If you take a standard size home, you make it Energy Star, it gets more efficient, the consumption goes down. But you could actually make a home that uses far less energy by simply making the building smaller, even if it was still built to the building code. Even if it had none of the Energy Star features, that building would consume less energy by virtue of its smaller size. So this is a key factor in looking at zero energy consumption, is you want to measure everything based on its consumption, and you don't really care so much about the quote-unquote efficiency. Another thing that we like to promote is simplicity in general, and that generally means sticking with techniques and materials that are tried and true. Now, that doesn't mean that we are going to do everything the way that a conventional builder does, because the whole point of this is making some very carefully selected changes that get the most bang for your buck. These are changes that have the greatest impact at the least cost. But generally speaking, you want to ask your builders and designers to do things that are not too far outside of their comfort zone. Everybody can be more efficient within the range of the things that they already know. In most cases, that's going to mean that we're sticking with standard wood frame construction, at least for now. There are proprietary systems such as structural insulated panels or insulating concrete forms. Those are great systems. They have lots of great benefits. But generally, when you go out to bid, you'll find that those are more expensive than standard stick framing. Now, I certainly encourage you to do that, to take your design. If you're interested in those systems, get an estimate, by all means. But be prepared to choose wood framing if it comes back to that being the least expensive, especially if affordability is your main goal. It's really important to keep in mind what is inside the building and what is outside of the building. The thermal boundary is that place where the insulation and air barrier exists, so that it keeps the warm air in and the cold air out, or if you're in a cooling dominated climate, it's the opposite. But basically, you want to be able to identify what's inside the building and what's outside the building. For example, a ventilated attic is generally outside. A ventilated crawl space, generally outside. A garage could be inside or outside. Basement could be inside or outside. The point is that you need to identify where your thermal boundary is and then make sure that you treat that very carefully to prevent an exchange of heat across that boundary. This is especially important with the heating and cooling system. We're going to talk a little bit about this later, but let me just say that your heating and cooling system should be inside the thermal boundary. And this means that if you have a forced air heat, that all the ductwork and the furnace should be inside the building, not in the crawl space, not in the attic, not in the garage, but inside the thermal boundary. Here's some free energy for you, a way to make buildings efficient by spending not a penny more. All you have to do as a designer is think about putting your windows on the south side of the building. Put your living spaces on the south side of the building along with those windows, and therefore those spaces will be more comfortable in the winter, and it will prevent the overheating from having a lot of windows on the east and west. So a southern orientation is always a really great idea in order to save energy, but also to save money. Now, it doesn't mean it's an essential element of all zero energy homes, because not every site has the capacity to do this. But if you do have a good sun, and even if you don't have great sun, but you have kind of marginal sun, might be a good way to save some energy without really spending any money. All you have to do is put some thought into it. There could be as many as 100 different people working on most construction projects. So it's really important to communicate clear expectations and make sure that everybody's on board. And what I like to suggest is that people think about having a number of checklists so that all the important features, all the equipment specifications, all the things that are really going to make the difference between your house being conventional and zero energy, all those things are written down on a checklist, and everybody gets a copy of them. This is also true for your subcontracts, the contracts that your general contractor has with the trades. Those trades need to have a scope of work that includes everything you want to happen, because if it's not in the contract, sometimes it doesn't happen. Don't rely on verbal agreements or general ideas. Create very clear expectations, put it on a checklist, and then use that checklist to make sure everything gets done. Let's look first at the shell. Just a real quick look at a couple of different ways to make the shell more efficient. The walls tend to be the most troublesome because there just isn't a lot of space there for insulation. So there are really two fairly well accepted methods for increasing wall insulation. One is to put a rigid insulation sheathing on the outside of the building. This can be either an inch, 2 inches, 3 inches, 5 inches, depending on what kind of R value you're shooting for. The other method is to use a double frame wall, a double stud wall, and that simply creates a cavity that's deep enough to give you the insulation that you want. You can go anywhere from an 8-inch cavity all the way up to a 12-inch or even deeper cavity. The point is that you're trying to get to an R value that your energy model tells you that you need. And that's in most zero energy projects in North America, that's going to be somewhere between R30 and R40. If you get up in the higher latitudes, that could be as much as R60 walls. Both of these methods work pretty well, and in my experience, the one that works the best is the one that your designer and builder is most comfortable with. So either one can be very cost effective, but it just depends on who's doing the work. If you ask somebody who normally does a double frame wall to do foam on the outside, they probably won't do as good a job as if they had done the method that they're used to. So trust your designer and your builder to do the thing that they are most comfortable with. If you are the designer or builder, stick with the thing that you're most comfortable with and don't try to do something different. In either case, if there is cavity insulation involved, it's better to use blow-in insulation than bad insulation. It's well worth the little bit of extra money you pay in order to get a little bit denser material, a little bit higher R value in the cavity, and also a reduction in the air leakage. Air sealing is still one of the most cost-effective ways to improve the performance of a home, and there are many ways to approach air sealing. A lot of it has been kind of the belt and suspenders. We're going to seal this and seal that and try this and try that, and then you get to the end and you do a blower door test and hope that it comes out really well. We're really shooting for an air leakage rate of about 1 to 2 air changes per hour for a good zero energy home. You can certainly take it lower if you can do that cost effectively, but I think that what we're shooting for in this 1 to 2 air changes per hour is very doable. There's a new product on the market now that can simplify air sealing. I like to mention this because air sealing can involve multiple people at different stages of construction. It gets to be fairly complicated about who's going to do what, and it's easy for things to fall through the cracks, no pun intended. But this new system called AeroBarrier concentrates the activity for air sealing into a single trade that comes at one time during construction and can pretty much guarantee a specific level of air tightness in the building. They do this by putting a blower door in the building. They pressurize the building, and then on the inside there are these little emitters that emit a mist of air sealant. And as the air escapes from the building, it's being pressurized by the blower door. It's blowing air out all the cracks and penetrations. That mist starts to collect on the edges of all these little openings, and after a couple of hours you can basically seal up the whole building. Generally, you do need to continue to do the basic caulking. The AeroBarrier will work on gaps and cavities that are 5/8 of an inch or less. So the large openings still have to be treated somehow, but the smaller ones can be done in this way, and you can really dial in the amount of tightness that you want. So a good thing to consider going forward. A lot of people are interested in spray foam for a kind of a quick fix to make the home both airtight and very well insulated. It does have the closed cell spray foam products have a high R value. They're great for air sealing, but they do have some drawbacks. One of them is that they're very expensive, and the other is that they have a high global warming potential. And this is because the propellants, the blowing agents that they use, are chlorinated fluorocarbons, and they are greenhouse gases in themselves. And so as those gases escape, they go up in the atmosphere and they create some problems that way. So closed cell spray foam tends to have this problem. There are a couple of different options. Some of the water-blown foams do not have this global warming potential, but they don't have the great R value either. There is a new product called Solstice from Honeywell, and it has a global warming potential of just 1, so it could be an option for using closed cell spray foams. So here are some thoughts about windows. The first step with windows is to just put as many of them as possible on the southern side of the building. That way they don't overheat in the summer, but they do gain some heat in the winter. It's pretty simple. The other thing is, how expensive do you need to go with windows? Windows can be a very expensive part of the project, and in many of the high performance homes that you read about in the magazines are using European, triple glazed or quadruple glazed windows that cost more than a luxury car. If you want to make your project affordable, one way to do that is to be real careful about your windows. Start by selecting the best double glazed product that you can find. That's going to have a U value of around 0.25 or maybe a little bit lower. That's a very economical window. So to start with, you're going to save some money there, and your energy model can help you figure out how do you need to treat the rest of the building in order to make up for the maybe a little bit more heat loss through the windows. But here are a couple of other ideas. One idea is simply to reduce the amount of glazing that you have in the building. It costs a lot less to build a wall than it is to install a window. So if windows are more expensive than walls, you can reduce the window area. You'll not only save a lot of energy, but you'll also save some money. When we talk about window area in a building, we use a ratio of window area to floor area. It's just a way to express how many windows are in there. A large custom house may have a window to floor area ratio of as much as 40%. That's a lot of windows. A production home, a spec home that you would buy from a production builder, might have a window to floor area ratio in the low 20s. So they've already reduced the window to floor area ratio a little bit. A custom home that's really trying to be super energy efficient, like the home that I built a couple years ago, we have a window to floor area ratio of 16%. You can reduce the amount of windows without sacrificing the values that those windows bring. It's the ventilation, it's the light, it's views, it's egress. All those things can still be provided in a lower window to floor area ratio if you're very thoughtful about where you position the windows and think a little bit differently about how you arrange windows and site them. So for example, we have some windows that are high windows and are horizontal, like the one pictured at the top of this slide. And what that does is allow a lot of light to come in, but since we have neighbors on both sides of the house, pretty close to us, it also gives us some privacy. So if you think about the placement, the sizes, shapes, and placement of your windows, you'll be able to reduce the size without sacrificing that. The other thing that you can do to improve the amount of light that comes into the house is to share light between rooms. So use a transom or French doors, say, with a glass in them to separate rooms. Those kind of things can allow light to go from one room to another, and you don't have to have quite as many windows on the outside. When homes get super efficient, and especially if they're a little bit smaller, they have a very low heating load. That's part of the idea. Unfortunately, a lot of the conventional heating and cooling equipment out there doesn't get small enough to service these homes efficiently. You don't want a big furnace in a small house because it'll just turn on and off. That's called cycling, and it'll cycle over and over again, and that's not good for anything. One of the answers to this is to use ductless heat pumps. These are small heat pumps. Sometimes they're called mini split heat pumps, and they don't have any ducts. Instead of ductwork, they have a unit on the outside, a compressor on the outside that captures heat from the outside and pipes that in through a refrigerant line to an indoor unit. And that's where the heat is exchanged from the refrigerant into the indoor air. And since it's a heat pump, it'll run in reverse and it becomes an air conditioner. The mini split heat pumps can be very small, properly sized for a small, efficient house. One of the issues with heat pumps is the mini splits especially is how do you distribute the heat? If they have a single indoor head, then it's a little bit difficult for that heat to go into the other parts of the building. There are a couple of things about this. If the building shell is super insulated and very tight, a little bit of heat goes a long way, and you won't really have as much problem distributing the heat because it will the building will tend to equalize in temperature pretty well just from a single head. But it's also, if you get a house that has different rooms and it's a little not quite as open, you might need to put in multiple heads. And these systems are designed to take multiple heads in different rooms if you want. You can also buy a number of different styles. Not all of them hang on the wall. Some of them are recessed into the ceiling. That's called a ceiling cassette. And you also have mini air handlers that go into the drop ceiling or a soffit and have a little bitty blower that kind of services more 2 or 3 rooms at a time. So talk to your heating contractor about mini splits and how to get that heat to distribute to different rooms within the house. Another method that's been used with some success is to use a small transfer fan and a duct to blow conditioned air from one room that has a head into another room that doesn't have a head. So say you have a really small room, it's kind of off in the corner, you don't think it's going to need very much heating or cooling, but it needs something. So this transfer fan and duct can essentially blow that air into the smaller room, and it doesn't need to have its own service. So those are some ideas for efficient space heating. The ductless heat pumps are used in lots of the more affordable zero energy homes. Ductless heat pumps are not the only way to heat a home, and some people feel like they need to stick with forced air. That's perfectly fine, but you have to put the ducts inside the building. And there are a lot of different ways to do this. You can go to a website called ductsinside.org and look at a lot of different information there. There's tons of other information on the internet that you can use to figure out how to do this. The key to success with doing Ducts Inside is to design it into the building. Designing it into the building means that your designer has to place the registers, has to place the ductwork and all the connections between there. And they also have to consult the heating contractor to make sure those ideas will work. So you really have to bring the heating contractor in early on in the design phase. You can't just, throw up the shell, have the guy roll up in his truck and expect the heating contractor to get all the ducts inside. It has to be planned in advance. The website that I mentioned is a really great way to kind of get smart about how to make that happen. Every home needs really great ventilation. And as you tighten them up, the ventilation becomes even more important, in fact, essential. The standard approach to ventilation in a zero energy house or any high performance home is a heat recovery ventilator or an energy recovery ventilator that's ducted throughout the building. It gives a really great balanced ventilation. There's air coming in, there's air going out, and it also captures some of the heat from the outgoing air so you're not just blowing it outside. Unfortunately, heat recovery ventilators can be very expensive. They can cost $3,000 to $5,000, which can really blow a lot of affordable budgets. So a couple different things to think about. One is a spot ERV. A spot ERV really only addresses a portion of the building. You might need more than one of these. Generally, these are placed in bathrooms. They have ducts going to and from the outside, but no internal ductwork, so they'll only kind of ventilate a fairly small area, and they don't move a lot of air, sometimes 20 to 40 CFM, but they do move enough air to meet the standard ASHRAE 62.2 ventilation requirements. A new player on the block are these through-the-wall heat recovery ventilators that don't have ductwork at all. They're just a tube through the wall, and they can do small spaces. They aren't terribly inexpensive, but if you have a small home, you may not need very many of these, and that could be a good choice for an affordable home. I'd also like to propose something a little radical, and that is that we get rid of the heat recovery element and just stick with some really good balanced ventilation. If you have balanced ventilation, you can get fresh air in, you can take the stale air out, you could filter that incoming air, but if the heat recovery aspect is what's driving up the cost, then you can eliminate that cost by just not having heat recovery. And if you live in a fairly mild climate, I don't think that you're going to suffer too much in terms of the loss of that heat recovery in economic terms. I learned recently that the cost of ventilation is about $2 per CFM per year. And so if you have a fairly modest house, you may have a ventilation and ASHRAE 62.2 ventilation rate of 50 or 60 CFM continuously. That works out to be about $120 or $140 a year. You're not really justifying the cost of the heat recovery aspect, but you still need to get the good ventilation. And so that's where the non-heat recovery balanced ventilation could come into play. In zero energy homes, we've managed to reduce the space heating and cooling of the building to a very small amount. And so that means that water heating now becomes the biggest energy use in the building. And the way to address that is to use a heat pump water heater. These devices are very much like your refrigerator, but instead of pulling the heat out of the cabinet and blowing the hot air out the back, a heat pump water heater takes the heat from the air inside the building and it puts that heat into the water. So it does have a tendency to chill the space that it's in. This is why in most places you want to put the heat pump water heater in a buffered space, a place that's not heated deliberately. It could be an unheated basement, an unheated garage, the kind of place that stays, fairly warm in the 40s, maybe 40 degrees Fahrenheit, doesn't get any much below 40 degrees Fahrenheit. These systems will still run very effectively. Even though they make that space a little bit colder, they don't affect the temperature inside the building. You can also attach ductwork to these so that you're pulling heat from one space and blowing the cold air into a different space. So for example, if you didn't want to chill the space that it was in, you could blow the cold air outside and through a duct. Some people even talk about, using these devices as ventilators. They move about 200 CFM of air, and so they would probably over-ventilate a house, but you could basically use this as your ventilation system. If you didn't want to chill the space that the heat pump water heater is in, and you didn't have a basement or a garage, that kind of buffered space, you might want to think about a heat pump water heater that uses an outdoor unit. These units are called CO2 heat pump water heaters. They're fairly new in the market. The tank goes inside, but the unit is outside, so it doesn't really cool the space that it's in. In homes that are in fairly mild climates that have very low heating needs, you can use one of these CO2 heat pump water heaters to drive some kind of hydronic space heating as well. So you could have a single device that provides both the water heating and the space heating for a fairly small space in a mild climate. I think that space heating capacity is around 5,000 BTUs per hour in addition to water heating. So it's a really low load house, and some people have done that. Another option is to just buy a standard electric water heater and add a certain number of solar panels to drive that electric water heater. Now you probably will need anywhere from 4 to 5 additional solar panels. That could get pretty expensive, and on balance you may find it's more expensive than the heat pump water heater with only a couple of solar panels to drive it. Something that your energy model can really help you figure out. Lights and appliances are a pretty big category of energy use in zero energy buildings because we've reduced everything else so much. Needless to say, all the lights should be LEDs. They're the most efficient. But when you choose an LED, be sure that you're getting the one that's going to work best for you, because you're going to have to live with those lights for decades. The average lifespan of an LED light can be over 10 years, maybe 15 years, and so you want to be sure to pick the right one. First of all, pick an LED that's bright enough. Many of the early LED products were fairly dim. Be sure to look at the number of lumens of light output that the light is producing, and you probably want something that's over 800 lumens, maybe even 1,000 lumens for many of the normal activities within the house. The second thing is the color output of the light. It's called the color temperature. Most people like a warm color light in their house. That's more toward the yellow end of the spectrum. The warm white lights are what you commonly get from an old style incandescent bulb. But the cool white is more of a daylight, kind of a bluish color, and that can often be a little harsh for people. So be sure to pick a good LED and do a little bit of research before you grab one off the shelf, just to be sure you're getting the kind of light that you can live with for many, many years to come. The appliances are fairly easy to pick. I mean, you just look for the Energy Star label, right? Well, that's a good starting point, but you can also go to the website, the Energy Star website, and see the most efficient products in every category. And I'd encourage you to look beyond just the Energy Star sticker and try to pick the most efficient products in that category. One of the things that many people kind of cling to in terms of fossil fuels is the gas range. And that's been one of the biggest issues of keeping fossil fuels in the house. And we've seen a big advance lately in terms of induction cooktops. These are electric cooktops that are somewhat more efficient than a standard electric kind of element. It may be 20 to 30% more efficient than a standard electric cooker, but more importantly is it's very, very responsive. And that can give you the control that you're kind of accustomed to, and yet you're not using gas and you're getting good performance. One of the biggest energy uses in modern homes are the entertainment systems, the big screens, the cable boxes, the game consoles. Those things are worth looking at. If you're moving into a new building, try to reduce the energy use in those products. Some of these are now under the Energy Star program. Others, you'll just have to do a little bit of research. But don't forget the entertainment systems when you're looking at efficiency. All of those different elements of the building are really important. I suggest that you think very carefully about investing in the structure and function of the building as opposed to the cosmetics. Beauty is only skin deep, as they say, and a lot of the cost of a building is in the finishes, the countertops, the cabinets, the carpets, the trim, etc. I suggest that if you need to make some compromises on the price of the building, to compromise on the cosmetics first. I know that this is the part that turns a lot of people on, and it's the part that you see every day, but it's also the part that's going to inevitably change anyway. I suggest very strongly that you invest in the structure and function of the building rather than in the cosmetic layer. So now that you've gotten the building ready, it's a matter of putting some kind of renewable system on the building. This is where your solar contractor can help you. It is possible that you could have a wind energy system too. We don't see that very much, but it's certainly legitimate. It's just that most of the houses are going to probably pick a solar system because it's quiet and there's no moving parts and it's readily available. The cost of residential solar systems have plummeted over the last 10 years, and so there is a really great opportunity now to do this. So when I went through this whole process in 2015, we came up with a house that was about 900 square feet. We spent $180,000 on the construction of the building. That was, I'd say about 40% below the local market for homes, for new homes. It's really a fairly simple overall structure. It's R60 in the ceilings. The walls are 10 inches thick. It's a double stud wall full of insulation for R40. We used blow-in insulation even in the floor, so that 12-inch I-joist floor was able to reach about R44. We have the best double glazed window that we could find. Came in at a U value of about 0.22. The air leakage was 1 air change per hour, and I was really happy to get to that level. The space heating and cooling is a heat pump, a ductless heat pump or a mini split with a heating season performance factor of 13.5. That system will operate down to minus 14 degrees outdoor temperature. So we've been able to heat the house through all the winters without ever relying on backup electric heat. We do have a couple of small wall heaters, electric wall heaters, that we don't really use. The water heating is provided by a heat pump water heater, and all that runs off of a 4.3 kilowatt photovoltaic system, and it works really well. In fact, we have a little bit of extra energy. We were producing more energy than we could use in a year, and that encouraged us to go out and buy an electric car. We got a used 2015 Nissan Leaf, and we're about a year into the ownership of that car, and so far we've been able to power the car for all of our local trips and without actually purchasing any additional electricity for it. So we're really happy with that too. You're probably interested in how do I sort all this information out. And one of the things that I recommend people do is to choose a third-party certification program. The certification itself, I think, is valuable in terms of the resale value of the house. But the other thing that certification does for you is it gives you access to experts that are familiar with all these technical details, with products that are involved, and most of them require that you do some kind of an energy model. So your energy modeling step is kind of taken care of by doing the third-party certification. They'll also have someone come out and visit the house, inspect the insulation, the air sealing, the equipment to make sure that you're getting the elements that you're paying for. A lot of people say that they want to get off the grid, and I think that that's become more metaphorical than actual, because it's really better to be on the grid if you're in a zero energy house, because you can share your excess generation with your neighbors, and you can also draw on the grid when you need a little bit more power than you can generate off your roof. It saves the cost of batteries, and that can be not only a big cost, but those batteries need to be replaced very frequently. When you're considering a zero energy project, one of the first things you should do is contact the local utility and find out what is their net metering policy. What's their policy for hooking up homes with solar panels? And they vary all over the country, so there's no way to make any kind of generalization. But in most cases, you're getting a credit on your account when you generate excess electricity. That usually happens in the summer months when there's more sun, longer days, and that credit can often then be used in the winter months when the days are shorter and there's not quite as much sun. If you're getting a credit, then you're probably getting the retail value of the electricity. In other cases, you may be simply paid on a monthly basis for the excess energy, and sometimes that's not the retail value. So in any case, you need to look at the net metering policy that's going to govern the site where you're building and factor that into the economics of your decision. In some cases, the net metering policies may not be terribly attractive for the consumer, and in that case, you could consider some kind of on-site battery storage. And most of you are probably familiar with Tesla's Powerwall, but there are at least a dozen other companies that sell electric residential storage batteries. Mercedes, Sonnen are two companies that come to mind. And so you can look into those batteries as a way to optimize your energy use and your connection to the electric utility. Big utilities are also using that same technology, the lithium-ion batteries, to manage your renewable energy on their systems. So that can help make a difference and will probably encourage more utilities to promote renewable energy. One way to save some money on your construction project is to defer what's probably still the most expensive piece of the puzzle, and that is the solar panels on your roof. Build the shell of the building just like you would otherwise. Lots of insulation, great air sealing, good equipment inside. But get ready for solar, but don't actually put the solar panels on. There are some details that you probably need to consider when you're designing and building the structure in order to accommodate the solar panels. I won't go into great detail about that. I just want to point out that that's a great way to reduce the initial cost of the project. Consider also that right now there are some pretty attractive incentives for solar panels, federal tax credits, utility incentives, and those are probably going to be declining in the future as the solar panels become less expensive. So if the tax incentives are part of your financial picture, you probably would need to consider doing the panels so that you can capture those incentives now. They may not be available in a few years. It's not just about energy. Zero energy homes are incredibly comfortable. They tend to have healthier indoor air because they're tighter. The air flow can be controlled, and builders that do high performance homes pay more attention to indoor air quality. They're also very quiet. If you're living in an urban setting or near some noisy freeway, then that extra insulation and the better windows is really going to keep some of that noise out. The biggest advantage financially is that you will not have to pay for energy for the life of the building. And that advantage actually gets more and more important as we move into the future and energy costs get higher. Now let's move into a discussion of the financial side of this. The technology has already been fairly worked out. We don't really need to worry too much about finding solar panels or the insulation or the equipment needed, even though the equipment is getting better. Everything we need to build a home is off the shelf. The issues tend to come up on the financial side. Most people tell us that the initial upfront cost to build a zero energy home is between 5 and 10%. I'm going to show you some ways to think about this, that it's not really costing you more, it's probably breaking even, or it could even be making you a little bit of money. Let's look at the cost to own the home on a monthly basis. If you built a conventional home for $350,000, you have to pay principal, interest, taxes, insurance, and every month you get a bill for energy. Now, your lender does not consider the energy when they're qualifying you for a certain amount of loan payment, but they should, because you get that energy bill every month and you have to pay it. Let's say that you can shift money from the energy costs into the principal and interest. So your zero energy house could cost $40,000 more. You could be paying $390,000, and yet your out-of-pocket monthly expense is the same. It's just that instead of sending a check to the utility company, you're sending a bigger check to the mortgage lender for principal and interest. One way of looking at this is that instead of paying for an expense, you're paying for an investment. You're investing in a home that's more valuable and more comfortable for you instead of just throwing the money away. So cost of ownership is about the same, and yet it's a better investment. Another way to look at this is that the savings that you get on energy increase your buying power as a consumer. You are able to afford more house. Freddie Mac says that the average American spends about $2,200 a year, or $183 a month on energy. If you divide that by 12, you can use that $183 a month to pay a mortgage, the principal and interest on your mortgage, so you can afford about $2,000 more mortgage. When you talk to a lender or a real estate broker, they'll tell you that for every $10 a month in income, you are eligible for $2,000 more in mortgage amount. So there's a pretty direct relationship between the amount of income you have and the amount of mortgage that you can afford to pay and afford to qualify for. If you take that $183 a month and buy more house, you have $36,000 to work with. You can invest $36,000 more in your house, and that's pretty much what it's going to take to get to a zero energy house. Here's another way of looking at it. Here's a way that you can pay the entire upfront cost of a zero energy house in one action. So this little chart's a little complicated, but let me walk you through it. We're going to be focused on 3 columns: the size, the conventional cost, and the cost of a zero energy. So let's say that you have a 2,400 square foot house and you're going to pay $480,000 for it. That may be high for some areas and it may be low for other areas. But don't get hung up on the amount, because let's just look at this illustration. So if you have $480,000 to spend on a house, you've qualified for that much mortgage, then you could buy a zero energy house for $480,000, but looking to the left again, it would only be 2,000 square feet in size. So by reducing the size of the home by 400 square feet, you can cover all of the costs of building the zero energy house, and the savings of $183 a month or whatever they are going to go right into your pocket. Let's look at a different example. 1,800 square feet, $360,000. That translates into a zero energy house of 1,500 square feet. Most of the people that I talk to realize that could live in a house that's a little bit smaller than the one they've got. So if the average American house is about 2,500 square feet, they could probably live a perfectly happy life in a house that's 2,000 square feet. Myself, I raised a family of 4 in houses that were always below 1,800 square feet. It's definitely doable with some good planning. If you're designing a custom home for yourself, you have control over the size. And there are lots of ways to build houses that are smaller that live really well. If you're out on the market shopping for a home, you may not have control over the size of the house, but you do have control over the size of the houses that you look for. And as a consumer, you have a certain amount of power to influence the market to give you something that you want. Production builders have a really great way of getting the cost per square foot of a home down to look attractive to justify a higher purchase price overall. Don't fall into that price per square foot trap. Look for a house that's the right price, the right total price for you, and sometimes that means a house that's smaller is going to be a better value. Now this example uses a lot of assumptions. It's just for illustration. If you would like to see exactly how those numbers can translate into your own life, I've created this little spreadsheet where you can plug in some of your own numbers. This will allow you to play with the numbers and come up with the exact size that makes sense for you. Now, just because you can afford to do it in this way doesn't mean that the mortgage lender is going to give you the money. This has been one of the biggest obstacles to overcome. The energy efficient mortgages have been around since the 1970s. They are very seldom used because there's extra paperwork. And we know if you've bought a house recently, there's lots of paperwork and you don't want to add to that. So energy efficient mortgages really have never gotten a lot of traction. What lenders are starting to do though is to recognize that the cost of ownership of a home includes energy, and you can either take that money and throw it down a rat hole, or you can invest that money in your house. We're starting to see some attitude change among lenders, and the more people like you talk to them about this, the faster that change will occur. 2 places to look. One is the Home Style Lending Program from Fannie Mae, and the other is a Properties Assessed Clean Energy Loan. Now, PACE loans are specifically for energy. They'll finance 100% of the energy improvement cost, and they generally spread the payments out over 20 years. That brings the monthly cost of loan servicing below the savings that you get every month. And so if the savings exceed the cost, that is called a profit. That's been working very well in the commercial sector. It's available in about 12 states. There are only 2 states now offering PACE loans for residential buildings. That's California and Missouri. We hope to see that improve and increase. Another obstacle is the appraisal. Lenders sometimes say, well, the appraisal came back, it did not recognize the extra value of the energy features of the building. Well, that's something that we have been working on steadily over the years, and again, that too is starting to change. The Appraisal Institute has an appraisal addendum, an energy addendum, that allows you to record all the details that an appraiser needs to know about the energy features of the home so that you can capture that extra value. A lot of those involve costs, so it's important for you to try to track the itemized costs of the various features so that you can put it in the appraisal addendum and give it to the appraiser. Third-party certifications will definitely feed into this. If you get a third-party certification, be sure to keep the certificate. If you have a rating like a HERS rating or an energy performance score, a home energy score, those things can be relevant. And I encourage you to write a detailed narrative. Why you're interested in a zero energy house, what are the features in your house that make it a zero energy house, and how those affect your comfort and the value, and also how that fits into the local scene. If there are other houses that are doing this, you'll want to mention that so that the appraiser can have some place to look for comparables. You'll make 3 copies of this packet. The first copy is for your mortgage lender. Hand that to them with your application and say that you want to get an appraiser that is qualified to appraise a zero energy house. This is a way that you can hopefully find an appraiser who understands energy efficiency. There are several certification programs for appraisers, and Appraisal Institute has one. Some of the local nonprofits have appraiser training programs. And by insisting on an appraiser who is qualified to do an energy efficient home, you are more likely to get somebody that understands what they're doing and how to approach this. So the lender can request somebody with those qualifications, and you should ask for it. It's likely that the lender will not give the packet to the appraiser. So you need to have the second copy of that packet for when the appraiser shows up to do an inspection of your home. Hand that to the appraiser, give them a little spiel about how wonderful the house is, and hope that they incorporate those ideas into their appraisal. If you get the appraisal report and they don't include the value of the energy, then you can contest that using your packet as evidence. Say that these are the reasons why the home should be assigned extra value. The third copy of that appraisal packet is for you to keep for your own records, but also when you decide to sell the house, it'll help to document the extra value that you should be able to get upon the sale. That extra value has been well established by research in the marketplace. Some studies have shown that the extra value can be anywhere from 3 to 8% just for a standard energy efficient home. This is not something that goes to the level of being a zero energy home. You could expect a zero energy home, especially in 5 or 10 years when the concept becomes much more common, you can expect that value to be even higher. The other thing about energy efficient homes in general is that they generally move a lot faster in the market. I think in my life I've sold 5 houses. They've all been more efficient than the typical house on the market, and they've all sold within a matter of days, one in 12 hours. And so at least some people out there are concerned about this, and they'll target these homes and they'll move. Solar panels themselves have some value, and Lawrence Berkeley National Labs did a report a couple of years ago that actually identified that value at about $21,000 for a typical size solar system. So that should come back to you when you sell the home too. There are quite a few different types of financial incentives involved. They vary from place to place, so there's no way to really explain what those are, but you can find out what applies to your location by looking at the Desire website. So that URL, type it in, and you can really zero in on the incentives that are available to you. Zero energy homes are happening around the country. Just to illustrate this idea, I picked 5 developments, one of them in New York, there's another in Florida, there's one in Arizona, Texas has a bunch. There's many developments in California and in the Pacific Northwest. All these places are zero energy subdivisions or master plan communities, and it's really starting to take hold. Now, if you find yourself in a town that you're shopping for a home, or you're a builder or a designer and you want to create one of these communities, I think the market is ripe for that. So dive right in. If you are a builder or designer, I encourage you to go to the Zero Energy Project website, sign up for our directory of builders or designers. If you are a consumer and you would like to find a builder or a designer, this is a great place to look. We screen the people in these directories to be sure that they have experience and dedication to the idea of zero energy construction. So it should be a good place for you to identify a partner to make a successful project. There are many information resources on the site. One of them that I encourage you to go see is the 12 steps to a zero energy home. It's kind of the basics of zero energy design and construction. You can find that under the Getting Started menu. There are also 2 blogs that we wrote in 2018. One called A Roadmap to Building Affordable Zero Energy Homes. That one covers everything I've talked about today and then some. So you'll find some additional ideas in there. There's also a really great book written by Ann Edminster. It's intended for California architects, but it really applies anywhere. Some great ideas on how to build a net zero energy home. That's called the Zero Net Energy Primer. Too often we feel like we are impotent in the face of these powerful outside forces. We're just consumers. We have to take what the market offers us. But that's wrong. We can shape the future. Each of us has a direct influence over families, our employers, our businesses, and in our communities. Every time you buy something, sell something, design something, build something, you are moving the world in a better direction. So let's move the world toward a place where buildings are not a burden, but a contributor to a better life. Thank you for joining me, and I hope to see you at the Zero Energy Project website.